Hello, whoa, ho. Can you hear me? Do you see me on your screen? Yo, whoa, hold up. Are you there? I'm here. Can you hear me? We're connecting everywhere, across the different places all over where you be. Wherever you're seeing me, hopefully soon you'll hear the same thing. I'm sure everyone wants to hear.
Hello,
But we're
whoa.
just a matter of waits before we get there. Why? Because we gotta sync up everything in due time. It's just how we do, it's how it is. And I know you all want to hear me say, welcome to the show. That's right, today is 3D Change Perspectives. And I know some of you have been looking forward to this because it is the boom edition of dangerous devices. So, last episode we went over real life dangerous devices that specifically are not explosives. During the start of the last episode, we did show you a phone battery, quote unquote, explode, which it really didn't. Um, Instead, it lit up like a flamethrower, and that was the big point. Most batteries don't actually explode, so today it's all about the boom, baby. Today is going to be a bit of a roller coaster where I do want to change your perspective on like what a modern battery really is, fairly safe. But I'm also going to showcase some dubious practices in real life actions that could make any battery a potential explosive carrier. While everything I want to show you, I want you to get an understanding of the safety measures that have been basically put in place at the same time because, sure, they get in the way and they can be avoided, but many people just don't even really understand them or how they actually help. And I kind of want to change our perspective on three things at once today. I know it's a little bit risky, but I'm hoping we can get you there. Now, before we go any further, I'm pretty sure we have a sponsor we need to thank, and that is absolutely correct. I want to thank the sponsor, which is Shield Folio. Now, on my side over there, you see the little QR code with the shield. You can scan that anytime during today's episode and basically visit Shield Folio so you can see all the products and stuff they offer. Now, one of the big points that we like about them is they offer this little Shield Folio book. It is stone paper, so you can write all your good stuff, your secrets, your passcodes, your key phrases. I also use it for like website logins and stuff important like that. Anything I don't want to get ruined or lost because it's rip resistant, tear resistant, fade resistant. It's basically designed to last because it's again stone paper. So we really like it, and we really think that everyone should have a copy or one to use. So if you go use one of these QRs and go get a shield field today, use the discount code Bitcoin Live 20 to go ahead and grab 20% off your purchase um, because it is an awesome little bit of tech. And again, like I said, that is stone paper. I know that's not something you hear very often. Now, I am getting the chat set up right now. So if you're anywhere online and you want to interact or say hello, basically you can go over to YouTube and jump into the chat and appear right here behind me um, as it is now active. To make sure it's active, we do this little thing. Can you see the heart? Boom. That's chat. That's a chat. Yeah. All right. So thank you again, Shield Folio, for today's episode. Now let's go ahead and jump in before we go any further because I'm going to forget different things. Oh, yeah. All right, everybody. Thank you again for joining and showing up today for today's episode because I know it is going to be definitely a fun one. All right. We're getting going. Oh, that's the wrong one. Whoop, there we go. Back in space. Now, today, I kind of did hint at some of the stuff that we wanted to kind of go over and stuff last weekend or last episode, and so this episode should be a little bit easier for everyone to digest. We're gonna jump into it. We're gonna flow in through, and the ideal, I guess, of today's episode is let me feed you this info, and I'm also gonna give you the opportunity to follow along at any point that you choose. So while we're going through it, you're gonna see this little pop up, of a QR. Let's see if it pops up. Boom. You can scan that, and that is where we're located. So that way you can always find where we're bringing up this information. We have quite a few different proofs, and we kind of got like a handful of things we're kind of going to look at. So I'm going to start back where we started last week, or last episode, and that is this video. So basically, this is someone purposely causing a lithium-ion battery to break. They're stabbing it with a knife and physically interrupting the layers. All right. So we just saw there was some spark, right? As soon as it broke some layers, you're seeing some smoke. And if we let it go a little bit more, a little bit of vapor release. Something like that. Then you start seeing it boil off and peel. So now at this point, we're seeing basically the internal temperature of this container rise to really high temperatures just before some oxygen gets into the mix. Because once oxygen gets into the mix, it's pretty much easy to say what's going to be. See that flame, and it just gets big, and then it's an actual flame thrower that bursts through the bottom. So it was randomly spewing fumes, spewing out flames, which are actually fumes pouring out of it. So it's really a lot of materials trapped inside of a shell, right? And if we come back in here and we just, you can see that there's a lot going on, but it's pressurized output. So not quite a bomb. So we're gonna go into, well, how do we know what's in a cell phone battery? So we've actually seen this we've actually brought this exact image up before. On a different episode explain about inside of a battery, and this was back when batteries were replaceable. And as odd as it is, if the batteries of cell phones that were removable actually had better protection around them than the current unremovable batteries that are built in battery packages. So we see a positive side here and a negative side. Both have these little tabs to pull power in and out, but there's also separators between each side. And the one in between the two sides is probably the most important separator of them all. So we're going to go into that. So this separator, you see here, this is basically the same thing. It's just a slightly differentized image so we can see what we're talking about. So the separator actually has these pores, and it's porous. So stuff can go back and forth. And there's different metals and oxides and stuff. And that's kind of an important part here is what's inside your battery are oxide metals and electrons. And we're going to move these electrons back and forth during charge and discharge. So let's look at specifically charge and discharge. So you can see the difference. I think seeing the difference between these two kind of helps explain a little bit of what's going on. So during charge, particles, or these electrons, go from the left to the right. During discharge, they're going the other way around. So it is possible to have one set of these going one direction, another set of these going a different direction, all in the same cell. It is possible to have some kind of mixture like that. We can also see there are two different kinds of backplates, like one's got a copper backplate, one's got an aluminum backplate, which are well known for not liking each other. But I mean, that's really all it is, right? But I think that's kind of the important part here. We got light metal oxides and light metal carbon. All right, cool. I think that's a lot of words. Today's going to be a lot of chemistry. So I went to an actual chemistry guide. It's the UK chemistry guide, because they show some really great reactions. They've taken the things that I'm talking about, I want to say, and they're just going to showcase it directly. So what reacts metals with metal oxides? So let's look at magnesium and copper to oxide. Let's take a peek. See sparkling. I see massive flame. I see burst. There's a little bit of a burst at the beginning, but once the copper pretty much solidifies, it it's like a liquid mess. See what I'm saying? It's like a liquid mess of just torturous metals, liquid metals. So what about aluminum iron 3 oxide? So hold on, this one has a video .111. We did have all these video points set up, but we're having we were having some difficulties with the internet connection. Everything got reset. So let's see. Here we go. This is thermite, basically, right? Thermite reaction. One like rust and copper or something like that. Rust or aluminum. Yeah, rust and aluminum. Yeah. Here we go. So it's going to go from the sparkler to the thermite, and you'll see the difference. So that's sparkler, and then here's thermite. That's the difference. Thermite's very immediate. There's not a whole lot more going on. It's super high heat. And this is what thermite's really used for. Thermite's used for instantaneously welding giant pieces of metal. So we can see the reaction between them. It does form this red color, and so there is some color things going on involved with some of these reactions. And I know that doesn't seem important, but actually it kind of is in some cases where when a reaction gives out color of some kind or something, it's duly to be noted. It has something to do with something inside of it, right? And when we looked at that one with the phone battery, there's a lot of red and yellow. Not a whole lot of orange, no blue, no purples, no browns, no blacks, no white. Well, man, yeah, there was some white at the base, like most, but I mean, like, there was no solid white flame or invisible flame. So it's kind of important to notice the differences in these different things. So this is going to be magnesium burning in CO2. So this guy is going to take, this right here is magnesium metal. He's going to literally catch it on fire. You notice it's in like little ribbon strands, so it can be caught on fire, so to speak. And he's going to put it into a gas. And it actually gets brighter when he does that. Now, he's going to take, because it's carbon dioxide is what that gas is. And you see it's building up in between the layer. Now, that's petroleum burning on that rag. He just put it in there, and the petroleum, and he can't even use the magnesium to light it, is what he says. He says the CO2 puts it out, and the magnesium that's burning inside there will not light it. So it's important to point that gases, even as little as they are kind of important. And so there's this thing that we're going to be doing today where we're going to try to see, can we generate a gas on the fly that might have, I don't know, the ability to increase the burning temperature of whatever's burning? That's one of the goals of today. Oh, wait, no, hold on. Whoa. I got a little bit out of, my bad. My brain told me there's more, but I forgot there's more on here. So there's actually an entire section here where it shows us a reactivity series. And if we go through here and we just look at specifically in this order, lithium, calcium, magnesium, aluminum, carbon, zinc, iron, hydrogen, copper, silver, in that exact order, well, that's a key somehow. And at this point, it sounds crazy, so hear me out. Some of this is already in batteries. We just need to find the right 1 to 3 materials to attach to a battery to get the reaction we're looking for. Now, I did say we were going to try to figure out how to generate a gas on the fly, and that's what I'm talking about, using a cell-phone battery or common cell-phone battery, and some other materials that if we was to then force a thermal reaction or it to go, like we saw earlier, the person just stabbed it, that it would produce a gas that would then increase the temperature of whatever we're burning. Perhaps we can use this to, like, to be honest, real world situation of this is like being able to fuse metals, strong metals, hard metals, metals you wouldn't normally be able to do, or maybe you just don't have the right tools for the job. So one thing to point out here, magnesium is above copper, aluminum is above iron, carbon is above copper, and magnesium is above carbon. Like there's this point where if you go too far away from the list, things won't work. For example, will zinc react with copper to oxide? Yes. Zinc is above copper and then will react. Will silver react with aluminum oxide? No. Aluminum is a long way away from silver, so they don't react. Will copper react to hydrogen oxide? No. Copper is below hydrogen and does not have reactivity to it. Does potassium react with water? Yes, violently. Okay, so kind of help you understand what all that means. So some of the stuff we have to do in sets, and be careful of what those sets are. All right, cool, cool. Let's go back to the next one because I said some of this is already in our phone. What's in our phone? Well, if we come in here and we look around, we can see in the display we got lanthanum and some other stuff and tritium, stuff that don't really matter. Let's go in here and see. Casing has got nickel and gallium and titanium. I'm sure I'm saying these wrong. Magnesium and nickel. Now, nickel twice and magnesium, those are things we're going to need. We're going to need gallium as well. We got lithium, cobalt, and nickel right there in the battery. Perfect. We need all three of those. We got more nickel, neodymium. We might need that in terbium again, and that might actually be helpful to increase temperature. So basically, your phone battery inside of a phone has a little bit more danger potential than outside of a phone. Now, I haven't quite said it, but we'll get there. We are referencing a not too old of a recent event where stuff happened with devices and batteries. And so we want to stick to those materials, which let's just say the battery, lithium, cobalt, nickel. Let's just stick to the battery because all the extra stuff, like in this example, this really old example, by the way, probably pointless. So let's just look at batteries. What are the major forms of batteries that we have nowadays? And this is updated for most recent year. This is actually just a couple of weeks old, not even a couple of weeks old, just a few days old. This is a very recent article. So we have lithium cobalt oxide, LCOs, lithium magnesium oxides, or LMOs. We have lithium iron phosphates, or LFPs. And then lithium nickel magnesium cobalt oxide, or NMC. Now, I mean, that that takes up like a third of our list right there. Boom, one battery set that we can find. There's a third of the things we need in one battery. But then they got lithium, nickel, cobalt, aluminum oxide. Ooh, 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 I like that. And then we also have lithium titanium oxide. That's going to be a good one to try for. Or even, oh, no. LCOs aren't here. No. We already said those. So, the main ones we really care about, I think, are these top three, though. Lithium cobalt oxide, lithium magnesium oxide, lithium iron phosphates. I think those are the three most common. The ones that you get nowadays, I believe this top one, lithium cobalt oxides, LCOs, while like lithium magnesium oxides and LFPs were more common like 10, 20 years ago. But they still are used, like in heavy, something you need a lot more voltage in, something with a lot more oomph behind it. So, well, you know, I can't just talk about the dangers of something without showing you the safeties behind something, because I did say there are safety stuff that people just don't seem to understand behind batteries. And well, this document it's mostly around high powered batteries, yeah, but it does show how batteries have become safer over time. Now I do want to actually give you the real PDF. So here's a link to the real PDF. And as you see very clearly here, it actually does state more that this is about EV batteries, high-powered batteries, hybrid batteries, but somewhere in here, if we was really dive deep in there, there is a brief section about how techniques in the cell phone, the mobilized battery technologies, how it kind of led to this point. And so it led, like, their improvements led to these improvements. So hinting at in the last 10 years, within the last 10 years, cell phone batteries have actually become a lot more safer. Cell phone batteries have become a lot more safer. I keep saying it that way because when we search into the nitty gritty of batteries, cell phone versus mobile batteries are like two completely different types of batteries. Cell phone batteries are designed for like extremely long use points, and they don't really are not really designed for being used at long periods of years at a time. Um, while mobile batteries are more used to short bursts of uses, but need to be available for like a decade, need to be able to be charged and recharged for 3, 4 decades. And so there's this huge difference in the battery forms. And that makes a difference in what materials are physically in there, as they kind of show in some of this data. Now, we're not really going to go through all this. I just want you guys to have this information so you can understand how. I can't just be talking about the dangers of batteries without showing you how they're safer in any way, shape, or form. And we have this is the full paper, and here, the one we were doing previously, is basically a generic rundown of the paper. So you have both. All right, now we're going to keep going because we got more to talk about. Yes, Brosiv. Damn. That is absolutely correct, sure. So when we come and we're looking at what causes the failure we want to see, we want to see because we want to use these batteries to generate a gas. We want to cause this. How is this being caused? What is causing these types of failures? And this is specifically over like the supposed like explosions, burnings, the flamethrower thing we saw earlier. This is really what it's about. Um, and let me double check my notes here because I am veering off course, but at the same time we're getting to the point, right? Because I know some of you are probably actually worried about this right here, what this entire paper goes over, and I do believe somewhere in here it says, "Yep, here we go, here we go, here they are." So here are the things that we're looking at. We got this lithium layered oxide inside of cadmium with a solid state or solid slate edge. Then we got all these separators and electrolytes and things and materials and liquids and blah 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 and salts. And then we have an anode, which is like graphite, lithium titanate, different metals, oxides, and also a solid state edge. And so what causes these breakdowns is like natural power fade. So what that means is you keep your battery charged, but you don't use it, and it fades. And then you have a phone that eventually sits there with no charge, but it's trying to have access because you're like your phone or your device, even when it's off, it's doing little things to use the battery, and it's trying to. So it's using all that absolute absolute tiny bit. Or you see people, they were like, "Oh no, it's still good," and they turn on their phone back on and they try to use it again. Oh, and it dies. Oh no, it's still good. They turn the phone and get 30 seconds to use or a minute to use or 10 minutes to use. Yeah, that's power fade. Material degradation. Internally, the material will slowly eat away, especially the center core. Now, a lot of phones' batteries are designed with that center separated with all the pore sides to degrade before any other separator does. Because if one of the metal sides or any of the other separators go out first, then you can have a leak, and a leak can cause a fire. Internal short circuit. This is the most likely cause of 99% of everyone who's ever had a thermal runaway event. It's internal short circuit. And it's internal short circuit normally caused by charging, as we'll find out. So I like how they actually have a thing in here where they're like, even if you have water cooling, air cooling, there's a chance anything within inside the material altercation, the anode, the cathode, the electrodes, or the separator can happen to cause this problem. Okay, anything within that space can still cause problems. But they're also hinting here that your battery management system can cause problems, and your protection system, normally circuitry, can also cause problems. And then they recommend fire extinguisher if you do have failure. So I do like how they actually mentioned that in there. So if we come in here and we look at the materials, and this is, to me, this is the yeah. spot of the paper. This shows us where our metals are in reactivity to each other, basically. And we see we have our oxides and our phosphoruses and our lithium metal. No, no, my bad. Our silicon. We see our oxides, our phosphates, and our silicon are all somewhat overlapping each other. That means that there is some form of reactivity between that lithium metal and those oxides. Okay? And as long as we have phosphorus there, we have a way to help remove that potential. So we might be able to do something to help remove the phosphorus. And we do know for a fact that phosphorus does not like high heat. So that's, again, why we need the high heat. Why we're always looking for these high heats. Deny everything. Alright. Here's the actual, I think this is the review. Yeah. So one of these is the actual PDF. This is the actual PDF where you can download it and everything, or you can read it online. The other one was a review. So this is the same thing, just the actual thing. I always do both for you guys. Some people want the generic breakdown. Some people want the full breakdown, the actual data. I want to make sure you guys have both. So we're going to go into, again, looking at this. Now, I saw this, and I probably read as much of this as they would let me read because I don't have actual access to the full paper. And I just kept thinking, what? You can recover lithium, cobalt, and graphite from these things? What? Like, what? Like, it should, what? Does that mean the amount of lithium, cobalt, and graphite in here is high? Yes. But that also means that there's a very high chance that perfectly sustainable batteries that just absolutely live their life but don't swell up and stuff have no actual interaction with each other. And that's good. That means there's something in there most likely scrubbing out a lot of carbonate or material they don't want. So I had to look into the process of this because whatever process it is to get these raw materials out of the battery might be important in what we're trying to do. So the thermal treatment of LIBs, which by the way, LIB is just a lithium cobalt oxide based Li-ion batteries. So the thermal treatment of these LIBs in mass are at 800 degrees Celsius for about 60 minutes to separate the cathode compounds and reduces the Li content into its carbonates, which results in the effective dissolution of the Li content in distilled water as subsequent processing steps. So they're dissolving half of the stuff into water. The leaching of the carbon contents is symmetrically studied in different acid solutions with varying times. So then they use acid solutions to, as they're separating stuff, they use acid solutions to find the other stuff. And then it's been observed that the maximum leaching efficiency is about 99% of all the carbon to be achieved within about 2 hours using a molar nitric acid with additional of 10% volume percentage of hydrogen peroxide. Now that hydrogen peroxide mixture into nitric acid would be kind of difficult. And the fact that it's a 2 molar nitric acid, and that's very specific, means it's very pure. So the graphite content was recovered as leached residue from the filtration of acid leachate. The cobalt contained is precipitated to its oxalate using oxalic acid, which is then converted into oxide by thermal treatment. And it's basically the exact same thing. Now, one of the important parts that we get is a lot of this is done at room temperature. So when I was here, I was going through like this stuff right here. I was going through all this stuff because I can't read the whole thing. So I'm reading this stuff, trying to figure out how they got to where they got to. You know, I found a banger. Hell yeah, baby. I found a banger. Can the Li-Fi PO4 batteries catch fire? Pretty simple question, right? Pretty simple question. Whoa. What? Sorry, I just looked back and I saw I missed something that I thought I covered. There it is. Yeah. I did miss this. Okay. So back here in the paper, the actual paper, there's some more graphs. I looked over and it said figure 6 is the ideal. So we didn't even get down to here. Oh, yeah, the bottom part of figure 2 doesn't really make a difference. That's the lifespans and stuff like that of each one. In which LCO shows the highest content of material to lifespan. So LCOs are your biggest bet for having a high amount of content. But some of the older ones actually have the high mixture of content, which end up like, short lifespan, but the fact that it's got more material. So basically, this shows right here some kind of crush to the outer shell, a penetration to the shell, internal short circuit, overcharging, and over discharging. Also, anything that can cause overheating, including the thermal runaway thing. So, the ideal here is if there's any kind of mechanical abuse, internal short circuit. If there is any kind of electrical abuse, internal short circuit. If there's any kind of thermal abuse, internal short circuit. So, anything done to a battery 99% of the time causes internal short circuit, which, as you can see, immediately turns into a thermal runaway, almost always, once we have it, which then we get high temperatures, air, O2 release, electrolyte vapor, which is flammable gases, exiting when they can, but until then, it's just a cycle of temperature increasing, O2 having less room as the electrolyte vapors expand. Fast. Very fast. Alright. But if we go down here, we can actually see how different things, and like all sorts of different things, can get us to the exact same point. Right? So if we have reactions between the anode and electrolyte solvents, we can get to power fade. But the SEI layer can decompose. Temperature spike, thermal runaway. If we have rapid charging and discharging at lower temperatures than expected, we get some kind of formation on the inside, which causes punctures, and the separators, which causes an internal short circuit, which is a thermal runaway. If we have sharp or rapid charging cycles or manufacturer defects, so basically if we're using, like charging the phone a lot and using the phone a lot and maybe not letting it get completely closer to dead, maybe not letting it down to like 15-20%, maybe you're recharging it like 50-75% or something like that. So you're charging a lot, you're constantly going through it, you're constantly keeping it on and stuff, or general manufacturer defects like we saw in some of those Note 7s. Well, you have microfractures in the electrode materials, which returns into reduced battery capability and increased heating during use, which then in turn can become thermal runaway. Because again, anything done can turn to thermal runaway, as we see in this figure. Anything can turn to thermal runaway. And it says, figure 6, this is our goal. This is what we want to get. Temperature of operation over 100 degrees Celsius. Electrolyte decomposition, release of those specific gases with thermal runaway. We want those specifically together because we want to generate a gas from the burning of like all this other stuff, right? Now, it does say to go down to figure 12, so we're going to see, okay, basically, again, any kind of damage done or abuse done externally to the battery can cause thermal runaway. Here is just other ways it can happen. That's a mechanical failure, basically. So we get down to graphs where you can actually see the heating and differences. This is a nice one. But you can see like the different ways things can be construed onto that battery shape or container. And here they are showing proofs of them trying to do these tests and how they react and how they're handling everything. I think that's kind of cool. But then we get this model. So if we want these high temperatures, like 4, I know that it doesn't really explain a whole lot. It's just a line number. This curved line is line number 4. We want to get to high temperatures. Basically, Temperature gets higher as we go up, and the rate that we increase in. So this D to F to 4 is our where we want to find ourselves. Okay, T and R is the math that we're looking at. And although that doesn't really matter, da da da, but we can, if we was to go down and look for it, it would give us a compound to look for. Do you see what I'm saying? Like, it gives us kind of the chemical compound of what we need to look for. All right, then we have something to actually use. We actually have something to use. Okay, so now we're at the point where we were a second ago, right here, which is basically, can it catch fire? And we're gonna jump the gun, because there's a lot of stuff in here that means absolutely nothing. And they do teach you the words, stuff like that. So we want to get to here, facing the flames, and we want to specifically go over the myth busting section. Overcharging. Push one of these batteries beyond its design limit can generate excessive heat, potentially triggering thermal runaway. Short circuiting. A direct connection between the positive and negative thermals can cause uncontrolled release of energy, creating dangerous heat and fire hazards. So what these are fire hazards? Physical damage, puncture, crushing, or severe impacts can damage the internal structure of the battery, increasing the risk of internal short circuits and fires. Extreme temperatures. Putting the battery in extreme hot and cold for prolonged amount can cause stress on the internal system and risk fire. And basically, some of the material going from freezing cold to really hot in short amount of time actually causes degradation. It physically causes the internal structure to just disintegrate. So okay, so we're not gonna keep lying to ourselves and say no, these batteries don't catch fire. It's more likely your battery will catch fire than explode. Okay, and what we're really seeing is that okay, I don't really want to cause physical damage to anything. I don't want to be there. So we're looking at temperature and forcing a short circuit. Perfect. I think if we do an overcharge while increasing the temperature on the battery, we can probably cause that. And if we wait for that battery to be like almost dead while we're trying to keep using it before we start charging it, we might have a better chance of degradation. Okay, so what actually causes the consequences of an explosion with these batteries? All right? I think this is what everybody wants to know. This is what everybody wants to know. Okay. Where does it say? In general, lithium iron phosphate batteries do not explode or ignite. Batteries are safer in normal use, but they are not absolute and can be dangerous in some extreme cases. It is related to the company's decision of material selection ratio processes in later use cases. Although the battery material is thermodynamically and thermally stable and structurally stable, they are among the highest of all current cathode materials that have been verified in actual safety performance tests. But the possibility of short circuiting from material and battery is inherent and possible, and by chance, it may be the least safe version. Now they come in here and they point out the fact that solid phase phosphate, iron oxides, and lithium salts are, a complex heterogeneous reaction because they're very dangerous together. So this is what we're talking about. Thermal runaway. I've said it multiple times. I know you guys have heard it, me saying it. So let's enter this danger zone and look at thermal runaway. This is really the thing we're just reading about, and I said with the batteries in the last couple of years. But this is the problem that often, it's like less often than previously. But we can easily see here there are more than one form of this. Like there's actually like if I go and I actually scroll down, there's chemical, there's going to be a physical, there's all sorts of different ways to cause a thermal runaway. It's not a one-shot stop to cause it. And we see what it really is. It's heat, reaction, increase of reaction rate, heat, and the only thing that we're seeing is the stuff that escapes the reaction. So, one of the things it says in here to point out, it says, For a quick example, sometimes vapor batteries are dropped in bags with metal zippers and put in pockets with keys, and then the batteries get really hot and stop charging sometimes. This is the very example of physical engineering or of thermal runaway, because the metal touches both ends and causes a loop charge discharge event to send electrodes back and forth. Let me go back to that image so you guys can see what we're talking about. So we're causing electricity to try to exit. So it's charging out, or no, discharging. So it's going back the other way, and there's nothing for it to go. So then it causes it charge, so it causes it to go back in, and then it keeps going through this loop event, causing one charge causes the other discharge, which causes the other charge, which causes the discharge, and then until it just stays flowing continuously, goes crazy, and then just finds a way to escape the loop. Okay, so now that we've pretty much explained that, because I think that's like an important part to explain. Like, that's one of the most generic forms of thermal runaway, especially people who vape. They can't, they see that the most, where they put it in their pocket or whatever, the battery, and it gets hot, and then they're like, oh, sure. Um, and then it just stops working. Well, there's been a lot of research on what causes this. And, they're going to show us all the same stuff, and they're going to say all the exact same stuff. And keep in mind, like, there's a little video here if you guys really want to watch it to help explain this in broader information, but in better detail. I'm not going to give it to you, but I wanted you to have the ability that if you think this is something that scares you, I want you to be able to take your worries away. Watch this video. It's not that bad. Some of the problems here, a lot of older problems was internal buildup. And that's one of the things that we're going to look at. Internal buildup. Why is there not so much internal buildup anymore? There is, but isn't, and it's confusing. So let's get into it. The actual thing, right? So Lebanon explosions. Learn about supply chain attacks. Yeah. So, ooh, wait, hold on. What? What? I mean, scroll to the bottom. Yeah, I did. Okay. All right. So go back into here. Go back here. Go back here. Let's go back to these attacks, right? So, well, I know a lot of people want to know what it is. So here's the real reason why everyone's scared about this. Many people think thermal runaway causes explosions like what happened in Lebanon. There are various sources, including some non-public sources and public sources like Graham Penrose. We were able to confirm the batteries of the mobilized pagers and walkie-talkies were tampered via a tampered supply chain attack. Like, I know this kind of hints that there was a supply chain attack. I was able to get confirmation it was a tampered supply chain attack. So it was after they were made, before they were delivered. Although I can't confirm what exactly was used, we know approximately it was 7 grams of materials attached to or near the battery and circuitry, but not directly near moving parts. And it's good to point out that there are metal contacts and moving parts, so shock is possible in specific conditions. Very specific conditions. So keep that in mind. And I don't mean shocked like how we as creatures get shocked physically and emotionally, but I mean shocked as in there was some form of static discharge. So the batteries didn't just explode. Material did near the battery. My hypothesis is that the material was used to turn the battery into a material generation with almost immediate high heat scenario where the amount of substance created would be from air and water and the materials to specifically have this kind of very large explosive gas generation. The metals and oxides you would need. So keep in mind, this would be hard to prove, but give me a chance to try to do exactly that, the material used in these explosions were specifically to create a gas to cause a lot of heat very rapidly. Which actually, think about it, it's how a bomb really works, right? Alright. So the question here is to find out high. Let me get all this stuff off my screen. Here, we actually get to find out about hydrazine, dry ice, and some of the most fast expanding materials are actually vapors at room temperature. And many low ambient temperature just to begin expanding. So they start expanding before room temperature. And if we could trap hydrazine into like a foam, or better yet, I don't know if we could make hydrazine on the fly, and trap something like a solvent material into a different material that reacts only when under heat and pressure, then perhaps we have an idea of what was used. Because that's what the whole idea of this experiment, this thought experiment, is to find out what could have been used. And I think what they were doing was using something to force hydrazine production live. So if we look in here, it looks like tin and brass is probably our best options. Well, to be honest, lead and tin. Let's be honest, lead and tin. And if we go in here and we look, boom, 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 they got some fun math for you. But this engineering toolbox, let's go there. I think that has some potential. Now here, it's exactly what you want. It's going to teach you, linear expansion coefficient. Like, what's the linear expansion based on its temperature? So, for one of the first things I want to do is earlier we saw temperature at 600 degrees Celsius. Let's convert that so we know about what we're talking about in Fahrenheit and in Celsius. So we got to get it about to 1100 degrees Fahrenheit, 600 degrees Celsius, or just under 1000 Kelvin. Nice. Just under 1000 Kelvin. Nice. All right. So when we're looking through here, there's a bunch of materials, and if we keep going, it just gets more and more and more. And we can see stuff like lead is right down here, lithium right down there. So some of the lower temperature expanders are way down here. All right. Let me find my spot so we can keep on going. All right. So now we got to figure out what it is exactly hydrazine. Like, what is that? So this is hydrazine. It's a chemical. It can be lethal. Burns rapidly. Burns or completely vaporizes at atmospheric pressure or normal ambient room temperature. Capable of detonation or explosive decomposition or explosive reaction, but requires a strong initiating source, or must be heated under confinement before initiation. Whoa! A colorless, fuming, oily liquid with ammonia-like odor, flash point 99 degrees Fahrenheit, explodes during distillation. It traces of air are present. Oh, explodes if air is present. Toxic by inhaling and by skin absorption. Corrosive to tissues. Produces toxic oxides of nitrogen during combustion. Used as rocket propellant in fuel cells. So it's rocket fuel. It's a part of rocket fuel. Okay. So, okay. That actually, it's either rocket fuel or an ingredient in rocket fuel. That's okay. All right. Now I understand what we're dealing with. So, there's this thing. Okay. When I saw this, I was like, I got to at least showcase this. This is a little bit off track, but it kind of gets to an idea of what we're looking at trying to do. So we're looking for materials that react under low temperatures or under only specific circumstances to make the battery become a generator or explosive material that just happens to be worked with rocket fuel, hydrazine. So Wolff-Kaiser reactions are performed in a novel silicon carbide microreactor. Greatly reduced reaction times and safer operation are achieved, giving high yields without requiring a large excess of hydrazine. The corrosive resistance of silicon carbide avoids the polymatic reactor capability issues that arise when Wolff-Kaiser reductions are done in glass or stainless steel reactors, with only nitrogen gas and water as byproducts. This opens the possibility of performing selective large-scale canteen reductions without the generation of hazardous waste streams. First published in 2013. Wow. Damn. So I did hint that we were going to have to trap materials. So this is really doable and like, wait, sorry. We did hint at trap materials, but we also want to make sure this is really doable in like a home kitchen sort of way. I asked this because like, I say this because like where the material would have been sourced and where it would have been and made or whatever or handled or in areas that are at best extremely remote and have, if you're lucky, something like electric stoves or ovens or maybe hot plates, and that's it. So this study basically shows, like in 2020, we knew we could trap hydrazine in silica type materials. Like, we already knew how. We already knew we could. Like, it's not a question of. It's just this is how it's done. Um, Waiting for it to pop up. So this part kind of caught me off guard. The explosibility of graphite powder. Now, I kind of had heard about stuff about these types of things, and the report provides data useful for quantification of graphite dust explosion risk in the nuclear industry applicable to operational and decommissioning activities. But specifically, graphite dust is what they're really talking about. I think that's kind of important. So it's not that it's just raw graphite, it's the fact that it's actually granulated graphite. So obviously, having some form of granulated graphite in materials, I don't know, that might increase in heat very rapidly, might not be the best of ideals. And yeah, so here's the lubricant material that contains a couple of the ingredients that are highly reactive under the right conditions. And this is dry or sometimes wet and oily bearing lubricant. And what else could it be used to lube or for? Basically, yeah, this is a graphite carbon lubricant. Yeah, this page takes a lot to run. It's a full PDF. It's pretty big. I'm just gonna drop it. All right. So I was doing searches, and I came across this page, which, as you can see, no longer exists. And if we go back to what it looked like, it said high performance scale inhibitor used to prevent the buildup of both carbonate and sulfate salt scale deposits. A highly calcium tolerant broad spectrum water soluble salt scale inhibitor specially formulated to prevent precipitation and blink inside of closed packages. Hmm, that's not. Wait a minute. That's that graphite. Yes, that's that graphite lubricant. 630 is that graphite lubricant. And, well, here's what it looks like now. It says almost exactly the same thing. It's a high performance scale inhibitor developed to prevent carbonate sulfate scales, including calcium carbonate, magnesium carbonate, calcium phosphate, barium sulfate, magnesium sulfate, and strontium sulfate scale deposits, because all of those are extremely uh, they like to expand fast. Let's put it that way. They like to go big, hard, all the time. Those things are like boom. So the scale inhibitor is a broad spectrum, high calcium tolerant. They changed that. It's not calcium tolerant, it's high calcium tolerant. Water soluble scale inhibitor, which has been formulated to inhibit the formation and deposit of carbonate and sulfate scales in oil filled brines. This is kind of important. It's designed to be used in an area you would never heat up. And that would probably be very, very wet. Inhibitor is stable at temperatures up to 450 degrees Fahrenheit. allowing to be used for products that may be thermally unstable. 450 degrees Fahrenheit is not very high. Not for the kind of pressures and stuff we're talking about. But it is a material, it's something that can be purchased, it can be sourced, and it can be made kind of easily. Um, and if we look, it's actually been used in batteries. Not only has it been used in batteries, it's been used in the exact type of batteries we're talking about. And one of the reasons why I bring this up, because at one point I had the document of this, but there was proof that the cell inhibitor used during the Note 7 battery explosions was actually the cause of those explosions. And from my understanding, that is how well, to be honest, that's how I got to this page. And now I don't have those proofs anymore, because they don't exist anymore. But this still exists, which is the paper that kind of proves they were doing it. And I did get I did save, like they weren't letting me on, so I had to save an actual thing, so I'm just gonna drop this off, because it's the same thing. Now we're gonna keep going, because, like I said, what else is it being used for now? So, silicon carbide graphite composite material. Silicon carbide graphite composite material. This is material that when you increase the temperature of the silicon carbide or this graphite, it's not going to be a good output. It's going to get really bad really fast. They don't like each other when they get hot. They don't like each other at all. So it's actually volatile. I had to look for my notes. Sorry, it's actually volatile under pressure and fire. So if we get a battery to ignite, like we saw in the video earlier, then we could make a semiconductor pop with this stuff, and because that's what it's mostly used with, according to this page. So I don't know. We'll get it to pop its top with some direct flame, theoretically, and which is now moving parts, and now more than just static shock. So good thing there's no metals involved like tungsten. Why would that be important? I mean, we saw earlier there are batteries with tungsten in it. Oh, right. This is why that dense inert metal explosions is an experimental type of explosion that has a relative effective blast radius. Is manufactured by producing homogeneous mixture of explosive materials such as HMX, RDX, and small particles of chemically inert materials such as tungsten. Whoa. Well, oh, high tungsten, low nickel, and cobalt, or iron. Well, maybe we're a little bit safer here because we don't have that much tungsten to have to really worry about, right? True, we don't have that much tungsten. But we do have a point of this. In July and August 2006, doctors at the Giza Strip reported unusual wounds caused by Israel Defense Forces, which they believed was Israel. That's who they believed it was, against the Palestinians, claiming that they were from previously unknown weapons. A lab analysis of the materials found on the victims' bodies was reported compatible with the hypothesis that dying weapons were involved. Israel denied possessing or using any such weapon. Basically, it comes down to an unknown force technically used these dying weapons. But it gets worse because, again, in 2008, 2009, it happened again, and again in 2014. Again with Gaza conflicts and Israel conflicts. Everyone claims they have nothing to do with it. So it's considered generally that some unknown actor decided to use them as a test, potentially. And it was said that there was actually the fact that like these wounds were announced and different things and for research and stuff after the very first, after the very last attack. So basically, once the doctors started talking about it publicly, those types of attacks kind of stopped. So, what's a pulsed chemical vapor dissipation of crystalline aluminum nitrate thin films and buffer layers on silicon and silicon carbide? Whoa, 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 wait a minute. Crystalline aluminum nitrate thin films as buffer layers with silicon and silicon carbide? We know aluminum nitrate don't like silicon carbide. What? So it's like all I'm really pointing out with this one is that there are ways and there are materials that have these exact mixtures we need of materials that exist in stuff. So we can purchase things that have this specific aluminum nitrate inside as thin films and with silicon carbide. I was like, okay, cool. We're halfway there. Um, and it says the very first sentence in there. Low temperature aluminum nitrate depositation has applications ranging from serving as a heat spreading material to serving as a buffer layer for 3-5 semiconductors on silicon and silicon carbide or radio frequency power and micro LED devices. I don't know if you heard that, but that's basically saying, that material we put down to help spread the heat on these stuff like your CPU, that material. That's what we're talking about. This one's with metal in it. Yep. Oh, here's the actual that's just the paper again, just in case I couldn't read because I couldn't read it earlier. We're getting into the aluminum nitrate. So this is just basically about aluminum nitrate. We're not going to actually go over it. I basically, like, every time I go over something major, there's a chance someone might find it cool, whatever. And if you do, here's some more education information about aluminum nitrate. Because, I don't really care about it, but some of you might think it's kind of cool. I don't know. I think it can, like, get you to do fire. I think firework people use it a lot. So, alright, here's that extra copy, just in case. So, when we're trying to figure out how to make this hydrogen. So, hydrogen decomposition over this big complicated thing. Model crystal prepared in size electric composition. So, half of this thing right here that we're looking at is that material we're talking about. So, if we put that material we're talking about on top of something with iron, well, that's good. That's what we're talking about. Okay, so hydrogen decomposition chemistry was probed over a temperature range of 100 to 800 Kelvin for a series of model crystals prepared for mass selection of iron and depositation on a planar aluminum oxide, nialuminal. I don't know exactly how to say the last part. And so, two sets of experiments were reported. Temperature programmed, blah blah blah, were used to study hydrogen decomposition inside the decomposition of this metal, and a material catalyst prepared for decomposition with the iron included, at density of approximately 5 times this negative centimeter formation, super small, super thin. Um, and it did create a catalyst to be found the hydrogen decomposition properties. Did this gas will break down specific metals. Cool. Not really. But what I'm saying is, producing this gas on the fly could also produce flaming napalm if we have the right metals involved. Nice. It's like a 2-for-1. All right. Here is hydroxamine. This is kind of okay. So basically, this is the salt version of the thing we've been talking about. This has ammonia with it. Okay. So this is like you can actually get a dry powdered type this. And it can be produced several different ways, and it's even produced naturally. And when we see from, like in here, there's a thing in here from nitric oxide, how to produce it from nitric oxide, it is the more favored form for what we need specifically, which makes hydroxyne to be a solid state in this case for us. And to get it to a vapor just requires quick temp change very quickly, not slowly. That's the key point here. We can get this in dry form and get it to vaporize to output part, basically what we need, but it has to be heated extremely fast. Extremely fast. Okay. And we can get this naturally. Keep that in mind. So, let's get into it. How do we actually make this out of air and water? Well, we're going to use plasma electrochemical cascading pathways. Technically, we're just using an electrochemical bath with plasma. That's the best way to put it. I do want to point out this was published this year. And the main part of this paper is that a better systematic way to do this was developed. So let's get into it. Here we developed a plasma electrochemical cascading pathway powered by electricity for sustainable hydrolyzing synthesis directly from ambient air and water at mild conditions. In the first step, the plasma treatment of ambient air and water delivers a nitric acid solution with a concentration of up to 121 mega somethings. Sequentially, the obtained nitric acid is selectively electroreduced. Electroreduced. I don't know how to say that. It's reduced with electrolytes and electricity to hydroxylene using a bismuth-based catalyst. Both steps of the PECP methods are operated at room temperature. And it's a yield rate of about 95.8%. Anything without this concentration will yield you less, though. But it still will yield. And that was kind of the important part. Nice. So now we know how to do it. We need to create a plasma. Well, we're going to need a solid piece of metal to create plasma with temperatures going from like 0 to 1500 degrees within a couple of seconds. Oh, wait a minute, that's what we're trying to do. Well, we have two plates, one on each side. We could create a plasma barrier of plasma. Even if it's only for a split second, we only need it for a split second. So salts of hydroxylene are prepared by reducing the nitric acid with hydrogen in an acid medium and a catalyst containing a metal from the platinum group of metals. And the activator selected from the group of metals, including copper, granium, cadmium, indium, tin, gallium, silver, arsenic, thallium, gold, mercury. Any of these reaction catalyst exhibits a high selectivity. Oh, so it can be any of these metals. Well, there's quite a few different metals there to choose from, boys. So basically, yeah, everything that we need does exist in the battery, except for just a couple of materials. Like, we're getting really close to, we get an older battery, maybe 10 years old. Bro, we might have everything we need in the battery, but maybe like just the catalyst and then the two things to jump the temperature up higher. Okay. Well, then technically we only need one thing to jump the temperature up higher, and we need something to control that. Okay. Cool. We got an idea of what we're going at. Recent advantages of bismuth-based electrolytes of CO2 reductions. Nice. Various bismuth-based nanostructural catalysts, including bismuth metal, bismuth oxide, bismuth subcarbonate, bismuth oxalate, bismuth bimagnetics, have been developed to enhance the performance of CO2, basically CO2 reductions. Typically, examples of electrolytic. Oh, that's exactly what we were trying to do, huh? So basically, if we choose this bismuth oxide that existed commonly in batteries about 10 to 15, 20 years ago, we have a real true hero here, which we were just pretty much discovered. So I'm just basically verifying that data. Here's a copy of what we just read. Let me get rid of that. All right. So what is this bismuth oxide that everyone's talking about? It's a versatile, high-capacity electrode material for rechargeable aqueous metal ion batteries. For rechargeables. Oh! This is that material that's used to help rechargeable batteries be rechargeable. Well, imagine that. So, this bismuth oxide really is in batteries already. I believe we really dived into one of these safety sheets. They pointed out that the material is selected for use because of its volatility, so that they are not normally in cell phones or devices that may get hot. Normally in low powered situations like pagers and walkie talkies. I mean, actually, pagers was specifically mentioned, I believe, in this article or in this paper. Um, so really high powered batteries that are constantly cooled. Oh, yeah, also really high powered batteries are constantly cooled because it's also used in like big EVs and stuff like that. But as we saw earlier, it's got to be dual cooled EVs. Um, but yeah, so neat. But this is the thing that stuck out to me. I watch EEV blog all the freaking time, especially on Odyssey, and I actually came across one of his community forum posts um, over exactly what we're talking about here, but they were talking about the ideal of using radio frequencies to distribute or to disrupt the volatile material within these devices that we're talking about. In this blog, many sources for showing the attack in Lebanon was a man in the middle. Actually, some of the sources came from this actual forum. So, if you want more sources on how we know it was man in the middle and all that, this kind of helps you out. They even come down to the fact they found out the batteries were like incorrect. They weren't the original batteries, or something was done with them. They tampered. There's tons of pages. You saw down there is multiple pages. I'm not going to all the pages. This is specifically page 4 um, of this talk. So it was a big one. It came down to no, you really couldn't use radio frequencies to do this. But if you had metals or something in there that's like could spark, but not like a regular spark, like a static spark, then yeah, maybe. And sure enough, the pagers had tactile buttons, and the walkie-talkies actually had a little movable thing that did actually could cause a static because it's two pieces of metal rubbing each other. So, what we're really talking about is something like a contact explosive. Um, Contact explosives is where the material goes violent and expands under very specific conditions. Because I can't find out exactly what was used, it's pretty obvious it's some form of compound like lead to iodine, nitrogen trititidine, silver nitrate, perhaps mixed with like petric acid or a flash powder, but then laminated with something like maybe quartz, hydrogen infused quartz, or testosterol, sorry, tetrafoil, tetratride. I can't say all these, bro. Tetrasulfur, tetratride. The outside material only being sensitive to shock and friction keeps the other materials from reacting early. But the outside material has to be able to wear over time from like heat and cooling. This needs to add the final material to create hydrogen vapor. So we need to be for it to be able to break down from heat and cooling, because that's what we're gonna do. We're gonna get it. Basically, it's gonna be cold all the time, and we're gonna heat it really fast. We want that change to create hydrogen vapor. So here are known types of contact explosives. Acetone peroxide. We can see it's sensitive to heat, flame, shock, and frictions. We see here it is an organic peroxide and a primitive explosive. It's produced with the reaction of acetone and hydrogen peroxide to yield a mixture of linear momentum and cyclodiameter, timer, and tetraol form. So basically, it mixes in ways it really doesn't like to stay together, and then they want to kind of explode out of proportion. They can't hold their form, in other words. Then we have chlorine azide, which is an organic compound that was discovered in 1908 and is unstable, and it spontaneously detonates at any temperature. So not the ideal situation one. We have copper 2 iodine, which we actually covered earlier. We looked at that earlier. Someone was talking about that earlier. So very possible chance there. We have fulminates, or chemical compounds which include a type of ion, and the ion is basically its charge relative to those of the hydrogens, blah blah blah. It's unstable though, and it's tended to be a type of salt, but friction sensitive. So it's not something we really want to fuck with yet. Okay, lead 2 iodide. Okay, this is probably one of the more ones. This is one of the ones I hinted at, right? So it's an inorganic compound, more than other iodines, and it's more than other iodines. It's explosive. It is more used as a detonator to initiate a secondary explosive. So this is a good possible core, right? With something else. Like, this is one of the other things I suggested it's probably with. Um, it's an organic compound, extremely sensitive. Uh, Small quantities explode with a loud, sharp snap. This is very important. Loud, sharp snap was actually one of the things that was like at the Lebanon attack. It was one of the very subtle points to the type of explosions they were. Loud, sharp snaps, and there were clouds, various different colored type clouds. We saw grays, browns, blues, and yes, purples. So there potentially some iodine vapor. So this is why I went with nitrogen tritiode, the triode, and then I suggested it's also mixed with something like petric acid, which is probably my preferred thing that it most likely is, just simply because um, this does not react with flame at all. So it will react with the shock initiator, but the easier choice is just flash powder because then, regardless of the static or the flame, it will boom. But if I remember right, flash powder is a little more like there's certain types of flash powder that's like more reactive to friction, while the butyric acid seem to be least in those points to reacting to friction. And also, the reaction of butyric acid isn't as reactive as like flash powder, but it does increase the energy quite a bit. All right, so then we have testosterone, testosterone, tetrahydrite. Ugh. It is a vivid orange, opaque, crystalline, explosive, and the most important binary sulfide nitrate, which are compounds that only contain elements of sulfur and nitrogen. And that's very important because it's easy to make. It's complicated, but easy to make. There's machines that do it for you. And yeah, that's actually one of the color materials that's one of the colors of materials that were left behind found was an orangey substance. Where we're assuming it has something to do with this. And I honestly think silver nitrate has something to do with this entire thing because it will just um, increase sequentially. This could be used as initiator easily because um, it wants shock. So if you electrolyte, if you had a static reaction to one of these other ones that was like this one right here, which then it causes a smaller bit of expansion, could be enough shock friction to cause like flash petric acid and silver nitrate to then initiate, to then cause the secondary initiate, to then cause the actual explosion, which is a large shout, a large sharp snap, and mostly energy with little flame. Why little flame is important? Because, well, if it's a battery, there's going to be a lot of flame. And one of the points and reasons why we wanted to create hydrogen on the fly is burning hydrogen creates the carbon dioxide and the water we need to put out the other materials that would flame. And so my honest opinion is that most likely the material was an even mixture of lead to iodine, nitrogen tetrahydride, with a tiny bit of silver nitrate mixed in. Um, with that, it's a laminate that has petric acid flash powder mixed into it, but the laminate most likely is some form of um, tetrasulfur tetratronite quartz or fused quartz or hydrogen fused quartz, which actually um, there was at one point. There's different ways. You know what? Let me just keep going with what I got in front of me, because basically the outside material is only being sensitive to shock and friction. This keeps the other materials from reacting. Then, as they react, it causes then more reaction, and we go from cold to hot, which then creates a different reaction, which then finally burst with the battery, because the outside material is going to react. The hydrogen vapor is going to react with the other vapors coming out as it's being created, which is going to then put out some of the electrolyte flame and some of the other stuff to get a very sharp snap. And shrapnel causes battery shrapnel, which we saw a lot of. in the situation we're talking about. So, this mass spectrometry study of thermal wireless of that stuff we're talking about over quartz ware and silver ware. Basically, there is a way to put that main material we're talking about with silver wool or quartz wool. Um, and if we're talking about we need both of those, well, guess what? It is basically possible to put the exact material together and trapping them into silver ware, just quartz ware, so that way we could use the tetrasulfur tetrahydrite filmed silver wool around our core material, then laminate it with the quartz, then did this again, we would actually create a material that is small but packs a punch. Now, have to point, this would be most complicated part of the entire process. The silver wool is a type of scrubber pad in your kitchen, though, by the way, so extremely easy to source. So then, silver nitrate, what you need to know. Um, it's dangerous. I want you guys to understand that. It's dangerous. Alright? There's a lot of problems with silver nitrate, but what can it be used for? Um, Silver nitrate can be applied to open wounds for wound care treatment. It's commonly found in two forms, as a powder, and silver nitrate sticks as applicators, which is very important. The silver nitrate sticks is probably the best part, because that is where we're going to get para from. One of the things we know we need. Because we saw that at the very beginning. Remember? That was one of the things we saw at the very beginning. Oh my gosh, because I have to go back and look. Okay. Okay. Most of what we are talking about today is talking common stuff you can probably find in your own home and then performing most this process right here. Light induced ring to chain transformations of sulfur, which can be done in your kitchen. It just takes a highly educated person and skilled individuals to create and form it. You could also do this in a backyard lab. Like there's a couple of YouTubers that do that. They could probably do this in their backyard lab. No joke. All right. So this is a screenshot from one of the proofs that we showed earlier, one of the links we showed earlier about the Lebanon explosion. Something I've been kind of just not giving you guys till now. All right. Let's read this together though. Israel is not conformed to either confirm or deny responsibility. Taiwanese company Gold Apollo, whose brand of pagers were used in the attacks, denied manufacturing with the deadly devices, saying that they had been made under license of a company called BAC. Gold Apollo CEO told these people in NPR that BAC had paid his company through a Middle Eastern bank account that was blocked at least once by his firm's Taiwanese bank, meaning his Chinese bank didn't want to do business with him at first. BAC, which was based in Hungary's capital, Budapest, has not responded to requests for comment. Citing three unnamed intelligence officials reported that BAC was an Israel front set up to manufacture the explosive pagers. ICOM, a radio equipment based in Japan, said it had stopped producing the model of radios reportedly used in the attacks about 10 years ago. It was discontinued, actually, about 10 years ago, and since then it has not been shipped from our company. Period. The production of the batteries needed to operate the main use unit was also discontinued, and a hologram seal, which if you would go back to the EV blog, you'd actually see proof of that, to distinguish the counterfeit products was not attached. So it's possible to confirm that rather the product shipped from our company. It is not possible to confirm the product shipped from their company. What this means is that the batteries were tampered. They were the batteries they needed. The batteries were over 10 years old. The radios, which had the silicone, the very specific caps and silicon chips needed to do this. Very specific. And that's the thing I'm trying to get at. Everything to do what they did. No one had been doing it for like 10 years or so. B, extremely specific amount of materials, specific types of materials, and stuff that was made in a specific way. The batteries alone were a decade old. The electronics were a decade old. Holding materials that were ideal for creating hydrogen on the fly, though, with a battery thermal runaway event. So not only we know there were added 7 grams of material to the battery in a way that was tampered and removed or damaged the original seal, then resent it as if nothing happened in the middle of their transit. So at this point, I'm hoping, okay, I'm hoping you see 4 major things. 4. So I can get my hands to look at me. 4. Batteries are not explosives on their own. Common batteries nowadays are not usable like ones in the Lebanon attack. Hydrogen can be made on the fly to make explosions heat amplified and at room temperature. The fear of anything with a battery being able to kill you is the more dangerous part of any device. Simply the fear of its potential danger. Over 10 years ago, many devices that have, I need to keep track. I'm saying, over 10 years ago, many devices that have batteries nowadays would never had them before. You would just been a plug and play. Many changes in many things have been to be able to scare you easier than before. So let me say this again. Over 10 years ago, 99% of the devices we have that have batteries in them now would have never had a battery in them. It would have been plug and play, low power, simple, easy to go. Now they all have batteries in there. And there's a reason. Think about it like this. The less you know and understand about your devices, the more room for fear anyone can have over you. Learn your device. Learn how to take it apart. Learn to look for rust, which is what's used in thermite. That thing we saw earlier, which is like, look at that explosion from earlier in that video. Learn to clean your electronics. Learn what is in your device. For example, one of the biggest factors of the attack we were considering involves having a bunch of semiconductors that most devices nowadays would never have. Most devices nowadays do everything they can to remove semiconductors from products or to drop down to like 1. Basically, the ideal of a semiconductor explosion is very dumb. Doable, true, but dumb to do because the material is very little in them. The amount of material is very little in them. And the 7 grams of material most likely is a silicone clay that was being used to absorb moisture. That's actually technically also, basically, they both most likely bought secondhand, used, discarded, fuel contaminated clay silicone mixtures because you can get it for research purposes, especially schools can. But I'm sure if you were like a city state or something like that and you were trying to buy a whole bunch for like your whole nation all at once, they wouldn't ask questions. But also mixed with common materials like metal shavings and powders. Most likely the tape used was the secret material that helped create the explosion. And looking back, we did cover 2 different materials that are kind of difficult to make, but they reasonably resemble Scotch tape, just not quite as transparent. These could be made in a backyard chemistry lab, and in no way is this being made with real tools. Still remotably makeable, yeah, you can still make this on the remote, but not in the real world sense of anything. The point of this is, well, sure, the materials exist, but so much has been done in the past 10 years because of attacks by unknown actors during 2004, 2008, 2009, and 2014 real life attacks. And they did show some how terrible some of these materials can be used that are being used in batteries of those days, not today, or not nowadays. If that makes any sense. Alright. In our first episode of this little mini thing, we went over the ideal of dangerous waves, which we found out dangerous waves are old technologies being reused in terrible ways. Reuse or recycle isn't always the best option for everything. Sometimes you need to actually recycle and get new proper devices for the new technologies you want to use. In our second episode, we went over the ideal of real life dangerous devices, which we found in real life dangerous devices are like USBs, power cords, charging stations, because our data is more valuable than the device in our hands. In this episode, we looked at the materials potentially used in the Lebanon attack, which we found it took decade old batteries, decade old materials, and stuff, and an additional 7 grams of material to actually turn a mobile device dangerous. Even though almost all the material potentially could and be made and set up in your kitchen or backyard chem lab. The reality is most dangerous devices is your own ignorance. And I do mean ignorance as in not knowing something. The dangers the dangerous thing nowadays is simply not knowing. So learn more and get yourself to understand what you use. Sure, you don't need to be able to build what you use, but maybe learn to repair it. Maybe that little step, because it's the best place to start after learning how to use your device. Because then at least then you can look for problems. You can clean them out or replace out potentially dangerous chips, caps, semiconductors for safer new ones. In reality, to get away from danger is to learn more about what dangers there are. Because the safety knowledge can save you more often than any government and law ever will. Because as sad as it is, the safety thing we pointed out at the very beginning of this episode, we pointed out to some safety talk that happened in like 2018 or 2016. No, my bad. It was 2015 it happened. Well, guess what? That safety talk is saving your life in more ways than one. And you could easily just learn how. And I think that's the part that everyone needs to get to. Learn how to repair your device. Why not? At least then you don't have to worry about the the ideal of it hurting you because you don't understand.